comma 1, 2, comma 4, 3, comma 9, 4, comma 16 is also data, right? So the problem is not the data, but the problem really is two things. One, uh, how do we clean the data, or rather, how do we know that the data is good? That is on one side. And the other side is, what is it that you want to transform the data to? Meaning, if we take the data, for example, 1, 1, 2, 4, 3, 9, 4, 16, the data is already transformed as the square of the first number, right? The question really is, can the system figure out 16 meaning I am telling it is 4, 9 meaning I am telling it is 3, right? So can that processing be done by the system? That's really the logic of the code, right? So what we are going to be looking at today is, we are going to see what is data in an astronomical sense, and we're going to see how do we clean data to, just have some sensibilities. And three, we are going to be plotting or visualizing the data, trying to see what does this data really mean, right? To many of us who think that, okay, why not spreadsheets, right? Where I can just draw, for example, sorry. For example, I can just plot a graph in spreadsheet. We will understand as we start seeing the data that it's just impossible just to do with spreadsheets. Okay? But before we go there, the way we are going to be going is, we will ignore astronomy for a couple of minutes. Let's look at data plain and simple, right? Let's look at data creation. Let's look at data visualization. Okay. Now I'm going to share my screen. So, but before I go, please do not be afraid of what I'm trying to do here. Don't think it's complex. It's when we actually sit down and look at most of the code, it's pretty simple for us to do whatever we are trying to do. Okay. So let's look at a very simple plot, right? The example being, the data of the example being this. So for example, I have a normal file that has data like this. It has an x and y coordinate whose values are 1, 2, 3, 4, 5, 6 in x and 15, 420 in y, right? And all I'm writing code here is a simple plotter, right? For the value of 1, my value is 15. For 0.2, my value is probably about 4. But for 3, it is at 100. But for 4, it is somewhere about 20. For 5, it's somewhere about 80. Right? This is a very, very simple plotter. Now, if you try to look at the code, all I'm saying is I'm defining what should be my height and width of the image. I am saying, should there be this outer border box there? And what is the file? Meaning, I'm saying here is the file from where you should read the data from. And then I'm just saying plot this as the x-axis and this as your y-axis value, and show me the plot. Right? Now, what we'll try to do is, let's try to modify the data. Let's say 7 is at 200, 8 is at 64, 9 is at 90, right? And then if I'm going to run the data again, you can see the plot changed, right? So it is very simple for us, assuming we have cleaned up the data and we know the data is going to be, for example, an XY axis, then this is super simple for us to plot. Okay. This is a very, very elementary example for us to understand what data can potentially do to technology. I mean, what technology can potentially do to data. Now let's go a little more beyond. When we talk specifically in the context of astronomy, location becomes a very important directive, right? For example, let's say I want to watch Venus, for example. Two things matter. One is, where is Venus, meaning the location of Venus. Two, from what location am I trying to look at Venus, right? Both these parameters matter. Now, how do we plot a very simple latitude, longitude, for example? I'm just defining the first value of latitude and the second value of longitude, right? And then I'm again calling it plot at this size. And then it's able to throw me some points on where all is this location coming from. Okay. Again, nothing very complex. And this is not even real coordinate system, right? This is just a made up x/y coordinate system. It's not the real GPS coordinate system. This is a very, very simple coordinate system that we are talking about. Again, you change this to whatever points and however it comes, and you're going to have the same kind of a plot. Now, let's look at one more example. What if, when we talk about astronomy, the most important thing is not an existing coordinate data, but rather how do I, for example, let's say we are figuring out the moon surface for the first time. How do we draw a crater of the moon, right? Or rather, how do we say that here is where a mountain is ending? Okay, at this point in time, we have a mountain like this, which is having a very deep dip, right? So all we need is, again, data points on how we translate coordinate systems on the moon. And I just have to do some basic manipulation where I'm just calculating min-max values over a period of 100. And then I'm translating them into weights. Weights is basically how much I value this data point, right? And then now I'm starting to define the grid points, which is, okay, here I probably have visited. Here I probably have a big rock where my rover cannot go, right? So things like that I can translate. And when I plot, I'm able to draw a line like this, okay? So this can potentially help astronomers, and this is really how, most of the space stations today are able to assist astronomers who go on moon on other planets, right? And they are able to visualize saying, okay, this is really how my surface is, meaning I can visit all the red data points. All the red data points are probably big rocks. So I should be careful. So which means if I have to go from point A, which is let's say 600, to point B, which could be let's say 7.5, 700, then my path has to be go straight, take a 45-degree turn, go for 200 meters, and then go straight, and you should reach this point, right? So it makes it easy to traverse data in it could be in something as simple as communication systems, or it could be something as simple as rover movements, etc. Right? So what is important in astronomy, for example, is how we translate data, right? Or rather, how do we interpret data to visualize what we really want to visualize? Now, this is all like very vague, really example data, right? So let's start looking at some real systems. I am going to be picking Stellarium here as an example, okay? So I have set the location currently to, I'm enabling ground, and let me set the location. If any of you don't know Stellarium, I think all of you should explore this tool. It's a beautiful, I'm setting the location as Kumbakonam, for example, right now. I'll set it, and if you see here at the date, we are on 5th February at 4:26 a.m. right? So 5th February at 4:26 a.m. This is how my night sky looks like from Kumbakonam. Okay, let's say I forward this. So what you can see really is I can see from this point how my sky looks like. Okay, so let's say this is the sun. I see that the sunrise is coming in. Okay, and I'm going to stop here, and let's say I disable atmosphere, right? Assuming at this point in time, which is at 8:45 a.m., if the sun was not there in Kumbakonam, this is how my sky would look like, right? This is where Mercury is, this is where Venus is, this is where Rigel is, this is where Vega is, right? Now let's come to something that is today. Okay, maybe I'll fast forward to 9th. You can already see how the whole thing transpires, right? Especially if you see, you can at this point in time see how various stars and constellations that we see in a typical night sky actually translate down to. And all of this, if we realize, is thanks to the data that we have collected all of these days. What you're seeing is an extremely higher order visualization of astronomical data. Okay, it's nothing more than that. let's come to today. We are on 8th. So 8th at morning 3 o'clock, this is how the sky looked like, right? This is the east, the sun is supposed to come out like this. And if I go a little fast, sorry. So Venus has come out, which means in a while the sun should also start coming in. And if you also keep observing this data, you will find some small dots. I'm not sure if it's going to be visible on the screen. Small, very, very small dots just like that pushing around, and they are basically the satellites, right? Right at 6 o'clock, and you can see the sun coming out. Okay. Now, this is also a beautiful version of astronomical data and how we are going to be looking at it. Right? I have enabled me to show exoplanets. I've asked me to show meteor showers. And I am also saying satellite hints, which is the small dots that, that keep going around. Now, what we will try to do is let's remove atmosphere again. Right? And this is really how it looks. Right? This is the point, this is the coordinate line that we are in. And if you look at the data, and let me zoom out a bit, this is really how it looks like, right? All the stars put together, this is how it really looks like. Now, let's say I enable also, yeah, I will also enable, okay, let's try to search for something, right? I'll pick some of the examples that I'm going to use today. Which is M33, for example. M33 is somewhere that side, right? Here you can see a highlighter. Now let's zoom in and try to see if you're able to find M33. And there you have it, right? So that's the M33 galaxy that we're talking about, right? Now, what is really happening here is there are three sets of data that's coming together to form this visualization. One is what we call as the time series data, which says at this point in time, this object is here, right? Which is the second data, which is the location data. So when you take at any point in time, let's say now at 10:30, 45 seconds at 800 milliseconds, Earth is going to be at this spot, right? Maybe at 49th second, Earth is going to be at this point, right? This is what we call as the time location series dataset. Okay, that's what we are looking at here. That is why I'm able to see at 8th February at 7:32:37 exactly that M33 is going to be here, which is from my point of view, which is the third data set. From where am I looking at it, right? What is my angle of view, basically, right? So M33 is obviously not going to be visible at this point in time. One, because of the light pollution. Two, it's probably way out of my the angle that I can look at, right? Let's, for example, look at M35. It's somewhere here, right? Let's probably look at, is there something that anyone wants to look at? Any specific object? Let's just say Saturn, right? Something close by. Right? And that's Saturn. Now let's zoom in. Can you hear me? Am I audible there? Okay, my screen is on. I'm sorry, 1 minute. Yeah. Yeah, sorry. I was trying to zoom in too fast. Yeah, so this is Saturn, right? What we can also see is the ring of Saturn. And what is important to understand from Stellarium is not just the three data sets that I talked about. The fourth important data point is the view angle. That is, in what angle from my point, let's say I'm standing here and Saturn is here, what angle and what rotation is Saturn in, what angle am I going to look at the Saturn at, right? Because I have set my location to Kumbakonam, for example, the only way I'm going to be seeing Saturn at this point is at this angle. right? So if we actually set up a telescope in Kumbakonam and look at it, this is really how I am going to be seeing Saturn, right? For example, let me change the location from Kumbakonam to, let's say, somewhere in Netherlands, uh, or let's say New Zealand, Australia. Okay, let me set something out of. Okay, it's all set to India, I think, by default. Uh, Let me just say any location preference. Let's just go northeast, maybe Assam somewhere. Okay, let's take a random location. Okay. Now, from a place called Akividu, you can see that the angle slightly transformed, right? It's not the same, but it is slightly transformed. I know this is supposed to give me location. Okay, country is set to India. I'm sorry. I will change this to New Zealand, for example. And we have the Griffith Observatory. Let's look at it. Right? You can see the angle of the Jupiter changed, right? So what you're looking at in Stellarium is basically you have a time and location series data, right? You have the angle of view from where you're looking at, and then you have your location from where you're looking at. So when you put all these four together, that is when you're able to see what you see on the screen here as the visualization. And what you're seeing as an image, right? Potentially what you should be seeing is just a dot, okay? But what you see as an image is a fifth data overlapped on it, which is the image data. For everything that we have gathered image for, we are just overlapping the data and replacing a dot with the actual image, right? That is what is enabling us to look at Jupiter this close, right? And if you see, Jupiter is already moving because my time is moving right now in this. But if I zoom out, I can, I'm able to set this properly. Okay, so I try to zoom in too much again, sorry. I have to wait for a second for my laptop to recover. Yes. Okay, so this is what we are talking about in terms of astronomical data, right? Now, let's come to our systems itself and let's try to see if we have to visualize something on our own. How do we do it, right? Can I have a basic code written to do whatever Stellarium is trying to do, right? Can I have a basic code that will help me do that will probably help me analyze Kepler data or maybe analyze asteroid data, right? So I have a couple of examples written already. Now let's start with trying to replicate what Stellarium is trying to do, right? This is a small piece of code that I have written. So what I'm trying to do in this code is I am trying to be an astronomer's helper, meaning a telescope's helper. For example, let's say today at let's say 11 o'clock, I am going to be in Trichy and I want to know if I can see M33. And if I can see M33, for example, what time can I see M33? What is M33 before we go there? M33 is the Triangulum galaxy, which is, at least, which is about 25 million, 14,000 light years away from India, right? So, what I'm going to use is a small library called AstroPy, which is a small library written for astronomical data analysis and visualization, right? So I am just defining certain defaults and just pulling in some code, libraries and all. So the first thing I'm setting is, I am saying I want to watch what is called as M33. I'll just zoom my screen to look better, okay? So I'm trying to say I want to look at M33 as where I am, and I'm saying my location, meaning my Earth location is Tiruchirappalli, India. What is this code going to do is it's going to translate Tiruchirappalli, India to latitude, longitude. Okay, and I'm setting the time as tomorrow 23rd. I'll change it to today at 23 hours, which is 11 o'clock. Okay. And then, sorry. And then what I'm trying to do is I'm trying to figure out what is the altitude and azimuth of M33, right? How am I able to do this is because this data is already public data, right? So this library has already read this data, which is the altitude and azimuth data, and it is able to predict in this given location at this time, M33's altitude is going to be this, which means it's going to be very, very close to the horizon, right? It's not going to be above the horizon. It's just going to be above, barely above the horizon, right? And then I'm saying I'm setting the midnight time to be at this hours. Again, I'll set it to 8, right? And then what I'm trying to figure out is I'm trying to figure out what is called as air mass. Meaning, is there going to be a lot of air mass that is going to probably have some level of deviation in what I'm trying to see. I'm trying to calculate air mass, and when I overlap air mass and the visibility data, meaning the visibility data is the time when this M33 is going to be visible, right? The plot I get is the plot I'm going to be getting is roughly about this time. I have to recalculate because it changed. Wait, let me just rerun everything. Give me a minute. Yeah, so for M33, roughly about 2 hours, right, which is probably about midnight, 2 o'clock is when we will start seeing, and at about 6 o'clock, because of light pollution, it's going to be gone. But this is going to be a translation window. Now, I want to coordinate this with the sun and the moon timings, meaning I want to know when the sun is rising, I want to know when the moon is coming in, and in between these two timelines, what time is M33 also going to be in the coordinate system where I can see it, or in the visibility system. So I'm calculating a couple of sample data sets of sun moon, which also I'm going to be plotting like this, right? And what I'm basically having here is I've translated the moon, I have translated the sun, and I'm taking over a range of 100 samples, which is 12 to 12, right? Meaning a good 12-hour chunk from the Earth's time. I'm trying to plot how is the sun going to transform, meaning the sun is obviously going to come around like this and go, which in a plot would be more like a sine wave, right? It goes down, comes up, goes down, comes up. That's how it's going to be in the plot, right? So I'm trying to transform this 3D layer into a 2D layer of a sine wave, okay? When I translate this sun moon and also the M33's data that I have, the plot I'm going to be getting is this, right? So the red line indicates the sun. Let me zoom in a little more. So the red line indicates the sun, the blue line indicates the moon, the dotted line indicates M33. So roughly about 2 o'clock is when is potentially what Stellarium is trying to do. And this is exactly what our simple piece of code has done, right? Roughly, if you put it all together, it's probably 50 lines of code, okay? So what I'm going to do is I'm going to pause for a minute to check if there are any questions, and then I will continue. Any questions from anyone so far before I go further? Okay, I don't see anything in the chat. I don't see anyone unmuted, so I will continue. So now this is one small example of what we are talking about, right? Let's the next thing that we are going to be doing is let's try to see Kepler data, right? So so Kepler data, the most important data of Kepler is the flux intensity or the light intensity, right? So what happens is if there is a star that we are observing, and if a planet actually goes in between, there is going to be a dip in the light, right? So based on that, we would be able to glean in information, right? So this data is available publicly. Let's first look at the data, right? Before we jump to look at the code. So please note all the data that I'm using is super small sample data. It's not going to be easy for me to look at every single data. Okay, the whole data set just using normal computer tools I have. Okay, so here is all the data of all the stars that is given here, and they have two labels. Okay, one label is called 2, one more label is called 1. And the definition they have given is each star has a binary label of 2 and 1. 2 indicates that the star is confirmed to have at least one exoplanet in the orbit. Okay, but 1 basically means there is no exoplanet in its orbit. Okay, and we have various flux state, and this is not small, right? So this goes, there are about 1023 columns. Sorry, about 1023 flux columns. And if you actually look at the amount of data points that we have close to about, I think, 5,600 or 6,000-ish, or I think 5,500 some. Okay, this is the sample data. We have about 500 data sets. Okay, so the first thing we want to do is translate and understand this data. Let's go through the code. Okay, as always, I'm just importing certain dependencies that I have, meaning I'm including certain softwares that I want for my code to run. Okay, that's all I'm doing so far. And once I am done, I have two sets of data files. One is called the testing data file, which is a small data set that I showed. The other one is called the training data file, which is here, which is also the same data, but a lot more data, right? Not a small set of 500 data sets, but much more. About this has, I think, close to about 5,000 data points, 5,100 data points or something like that. Okay. So what I'm basically saying is I'm going to be training my code to read the train data set to understand how is this flux changing, right? And then I'm going to be testing it on the small data set to see if everything is good. Okay, so when I put it, there are 5 rows. I have only told, show me 5 rows, so it's saying that. And there are 3,000 columns, right? Unlike the test data set that we talked about, the actual training data set has close to about 3,000 columns, 3,198 columns. Okay. Now, what we are doing here is I'm just trying to understand. Now, I have a certain set of data. I first want to know how is my distribution, right? Is my data distribution equal? So, for example, let's say I want my code to figure out if I give a picture to it, if it is a cat or a dog, right? So what should I have? I should give at least 100 photos of cats and 100 photos of dogs. Only then I know my code is going to figure out, okay, this always means cat and this always means dog. So this is called equal distribution of data, or data distribution has to be equal. Now, the first thing when you take any data point or any data in astronomy is to ensure if your data is actually equal and distributed well enough. Only then you can make predictions out of it, right? And if your data is not equally distributed, you should not make predictions out of them, and you should only visualize them to understand what you can infer out of it. Okay. Now, what I'm basically doing is I'm taking, this is my distribution, and if I look at this graph, right, the ones with label 1, which basically means star with no exoplanet, there are 5,050 data points, right? Versus the label 2, which is star with an exoplanet, there are only 37 data points. This clearly says that the data that is available to us is not equally distributed, right? Now, so which potentially means I cannot train my code to do machine learning analysis, but I can do basic analysis, okay? Meaning I can glean information out, but at the same time, I cannot use this data set to do machine learning or artificial intelligence based predictions of my data, okay? Now, that is given, what I'm going to be saying is, now take only those with the value of 2, which is stars with exoplanet, and just plot them. and show me. And this is how it says, right? This is all the 37 stars with their flux distribution plotted in a graph. Obviously, this is not visible, right? This is completely unreadable. So what I've done is I've taken only one, right? I've taken one single uh, star of the 37 and I'm plotting the flux distribution out of that. And if you see here of this data, this looks normal, but this data point that is between flux 2500 and flux 3000, you can see a good dip in the distribution, which basically means something passed by, right? Obviously, just this much in data is not enough for us to make a prediction saying that it was indeed an exoplanet. We need to, analyze much more longer data sets over a period of time. This is only at one period of time, meaning at one time, right? It could be, let's say, at 10 hours, 37 minutes alone, okay? Now, if I keep on analyzing this data at 1038, 1039, 1040, 1041 for the last 6 months, then if I consistently see a dip pattern, then I know that this star has an exoplanet surrounding it, okay? But what we are again looking at is a very, very, very minuscule set of data, a small set of data, which any laptop can without hanging process, okay? But when we have to look at really large data sets, we may need slightly powerful servers that will, sustainably run all of this, right? And this is really what the plot is looking at. So we can say that for star 4 of label type 2, we can suspect there is an exoplanet passing by. Let's try to do the same for, let's say, star 5. Right? You can see the data distribution is quite different, right? It is pretty static, which means there is probably nothing coming in between, right? Or there's probably something that is revolving very close by. Could be, okay? Again, the data is too small for us to make these predictions. If I take the 6th star, for example, it's pretty static, right? Again, it could be pretty static in this time frame. Please remember, we're talking about just one time series data, right? We're not talking about at least 6 months of time series data. From the 6 months of time series data, we're talking about one data line, okay? At that data line, this is predicting this, right? It could be other way in other data lines. Okay, now let's try to look at the ones without. Okay, you'll see a different plot. Okay, now let's say 7 to 9. Let me plot two of them just so that we can compare. This is, you can see that things are very different, right? There is a different plot here for the star, and then there is a completely different plot here for the star. So all that we had to do was to have a small spreadsheet like this, sorry, here, a small spreadsheet like this with all the data put in, and then we were able to plot all of this in just a matter of minutes, right? Now let's look at one more example. We'll take the same Kepler, but let's try to look at a little more slightly different distribution, right? Meaning so far we have been looking at a distribution from the star's perspective of a flux distribution. Let's transform this, meaning I want to look at the flux distribution of the stars. Okay? I'm doing the same, I'm doing the import, I'm using the same data files. It's the same set of data, right? Nothing I'm changing, I'm just defining certain plot definitions. If you think that all of this is very intense code, it's not really, right? I'm just saying, please display this as a planet name, the color is black, and the font size should be this, right? It's just defining how the UI should look like, meaning how I should visualize it, right? Nothing really complex is being defined here. And then when I go and pick, I am picking 5 examples, right? For this case, I'll just pick one in both, meaning one with a planet and one without a planet. Okay, when I plot it for flux 0, and this is my distribution on planet, and for flux 37, this is my distribution on planet. Okay, so so this is just a transpose previously. Previously we saw flux in the x-axis, and the star in the y-axis, right? We are just transposing that and trying to say my flux is my x-axis and the intensity of the flux is on my y-axis, and the star and the time distribution for the visualization is on the y-axis, sorry, x-axis, right? So when I look at it, this is how I'm looking at it, right? I can pretty much clearly say that on flux 0 for row number 0, this star exhibited some traits of an uneven distribution, right? Now I can do the same plot for maybe first 10 of them, right? And I would still be able to do, right? My first 10 plots are here, and then this is the one without, uh, uh, this is the one with transitioning planet, and there is one with no transitioning planet, right? So if you see the ones with the planet, you can all see a very clear pattern of this. Is there a question? Okay, please mute your microphone. Can you please mute your microphone? Yeah, thank you. Okay, so this is really how the data sets look like. Okay, now this is just again a very step 0 of what we are trying to do, right? But there is way too much data for us to sit down, analyze, especially if you're taking asteroid data, which is the one we're going to look at next, right? The data amount of data is pretty intensive. There's so much we can analyze and conclude out of these, right? So this I'm going to be taking from what is called as asteroid diameter prediction. So what we are going to be doing is we have a data set with various asteroids listed. Okay, I'm going to show the data here. So this is my data set where I have various asteroids listed, right? And various data points of the asteroid that is existing here. Okay, and this data is given by NASA, so I've just taken the raw data as is. And what we have been able to do here is is to look at all of this data. I'm breaking down this data into small sets. One, I'm saying learn from the diameter data. And the second thing, what I'm saying is, can you predict asteroid's diameter, right? If I give you the parameters of the asteroid, can you predict the size of the asteroid, meaning the diameter of the asteroid, right? That's what we're trying to predict here. Now, the definition of various data points is defined here, right? And all I'm doing is loading the data. Again, I'm saying what is the value I should be looking at, meaning what is my diameter value, and what are all the values that I don't need to look at, right? So, for example, full name, this, that, and all, I don't necessarily need to look at for my diameter prediction, right? And then I'm trying to say here, finally, you only the diameter data here, which is distributed like this in proper there are about 1,37,000 columns, which is completely cleaned proper data, right? And the maximum diameter value that is defined here is 939, and the min seems to be somewhere about 0.002, which could be just a small thing, right? And then when I'm going forward, I am training the data, right? So here what I'm trying to do is I'm saying, okay, and this is a machine learning example, right? Where again, this data is not great. Okay, this is really bad data, but I'm just showing this for the possibility of saying that what is it that you could be doing, or what is it that we could be doing. Okay, and what I'm doing here is I'm saying, okay, train from this, and this is my data sets that I have taken, and I am doing what is called as a random forest regressor, which is basically a machine learning algorithm to look at numerical data predictions and then learn from it. And then I am doing a prediction, okay, which says, okay, now when I do a random forest regressor, what it basically says is it does an algorithmic learning of numerical data. And then when I run a prediction, what I see here is this is the actual diameter, and this is my machine learning learned diameter, right? And if you can see that the success rate, which is my accuracy rate, with whatever super small data I have, I can say it's roughly about 70%, right? The data has been about 70% accurate, meaning the machine learning's predictions of diameter has been about 70% accurate, right? Uh, so this is some of the examples that I wanted to show to all of you, uh, just to see if this would probably inspire some of you to explore this as a domain of exploration. But again, so I wanted to make it again really, really clear because many times there is this misconception. What we are seeing here is again a super, super, super small data set and extremely elementary algorithms, right? We can obviously do a lot more detailed predictions, much better algorithms that are available for us to do many of these activities, right? Now, there is, so Chiguru is currently organizing exoplanet search program and also an asteroid detection program. And we are also having a couple of telescopes with us. So we are trying to gather much more of this data for by ourselves, right? Through either the asteroid search program or exoplanet research program. And what we're trying to do is once we have gotten access to various parts of this data, we are trying to do much more intensified data classification, uh, data learning projects, which potentially would help us identify and go towards auto discovery of asteroids or exoplanets and see if we can contribute in identifying many of these stuff, right? But it's not just restricted to what I'm again talking about is purely from astronomical object detection and existence, but the whole project is not restricted to this, right? I just picked this so that it's easier for us to visualize and understand. Now, there is radio astronomy data, there is photo astronomy data, there is general visual astronomical data, there is image data, right? There is various types of data that is existing. There's numerical analysis that we have to do. There is various types of data that is existing, and it is the amount of data is actually abundant, right? There is so much data available for us and so much we could glean out of it, understand it and process it, which is exactly what Chiguru is currently doing as a part of our research efforts, right? So if any of this sounds interesting to any of you, feel free to get in touch. There is enough work for us to be done in these lines, enough projects to focus on, enough data to review, understand, learn, fix, clean, enough algorithms to build again. Most of the data and algorithms we're using are very generic machine learning algorithms, right? Many of these algorithms could actually benefit from tuning these algorithms to be more astronomical specific, right? Where these algorithms could say that, hey, you know what, this data set is not enough for me. Give me at least 6 months of data to learn from. Give me at least a year long of data. Give me at least 10 years of data to learn from. And then I would be able to make predictions, right? But all of these predictions and learnings, while, is one, there is a research angle to the whole thing. What is also important is there's also an educational angle to the whole thing, right? How do we visualize this is a direct correlation of how well students are able to understand what we're talking about, right? If we say that, even if you take flux for example, instead of talking about the whole thing theoretically with random data, if you're actually able to download an actual data and run the code and help them visualize, right, amount of learning, or at least the difference in amount of learning would be really different, right? So that is roughly what I wanted to share with all of you. I can open up for questions. Again, largely I'm saying if any of you are interested in astrophysics, especially astrophysics and technology especially, please to get in touch. I'll put down my email in the chat. Uh, just to help all of you understand, I've been in the IT industry for about 9 years now. I've worked at various spectrum. I've worked with AI and healthcare. I've worked with AI and recruitment. I've worked with general technology. So I know the amount of intensity at which all of this data has to be trained at. And at this point in time, Chiguru can happily collaborate with many of you, whoever is interested in this whole spectrum, right? Chiguru would be more than happy to collaborate, and there is really, really enough work to be done.
Uh, Hello,
Yes, yes, ma'am.
my name is Dipali. Would you share this sheet, Jupyter Notebook, on any Google Colab or by Gates?
Yeah, I can publish it somewhere and we can get it sent out to you. That shouldn't be a problem. I mean, but all of this is just basic code. Uh, but yeah, I'd be more than happy to. No problem at all.
Okay, and second question from my side is that if you are doing anything with the solar physics, not with the astronomy,
Mhm.
stars, galaxy, not that, only with the sun. Because
Mhm.
I am a solar physicist, so I wanted to
Right.
interest in that.
Honestly, if you ask me, it is just a matter of, in my view, right? It doesn't really matter what we are focusing on, meaning what domain we are focusing on. What I am more interested in is what is it that we are trying to understand, and how much of data do we have, right? And then it is just a question of how are we going to translate the whole thing to make it sensibly predict or discover or visualize what is it that we want to do, right? So I would be more than happy to work. I mean, but assuming you can help me understand the data that's available, understand certain concepts of, how I should understand and translate this data to human language, then, it would be easy for us to go
Okay,
from
graphene.
understanding. Yeah, yeah.
Huh.
That
I
help
have
I
to
would
explain
probably
the
need.
physics, then you can do the machine, जो भी coding है, that code.
Sure, sure. Totally we can do. Yeah.
But I wanted to learn by myself.
Um, so there is one program, I don't know if it's still good to go, like Surinder, correct me, is we are trying to launch a program on how do we use many of these libraries to specifically for astrophysicists, right? So I think it's still in the syllabus framing phase where we're just trying to frame out the whole thing. So this is going to be at the intersection of primarily astronomy, right? We're not going to be breaking it down into various sections at this point, at least for the aspect of the training, right? So it's going to be general astronomy and technology, and whatever I showed you right now, how do we go from a basic hello world
हाँ,
to a good conversation, right? So that whole
हाँ.
thing we're still phrasing out as a training session. So it may take a while for us to come up with that, but if you can maybe give your email or something in the chat or to Surendra.
I
Uh,
will send you email just in few
sure,
seconds.
sure, yeah,
Uh, your email is in chat box, no?
correct, correct, yes, yeah,
Okay, thank you. You have to share this Google Jupyter notebook.
sure, sure, I'll do that. I'll
Okay,
share the
thank you.
Jupyter notebook as such. I don't use Google Colab. I have
No,
my
it's okay.
problems with
I
Google.
also using only Jupyter notebook also.
Correct, yeah, yeah.
Thank you. Thank you very much. I didn't see. Okay, I see your email. I get it.
Yeah.
Thank you.
Any other questions from anyone?
uh, Participants, you may ask questions, anything related to data or computer stuffs. Also, if you want to speak something related to astronomy, or if you are interested in data, like Professor Deepali spoke. So if you are interested in learning astronomical data stuffs, software, anything, you may ask. So the floor is open for questions and discussion. So we have enough time to cover many things. So yeah. If if you think the session is having some high level data kind of coding stuffs, if you're not really I mean you can't understand something, no, so no problem, you can ask like I'm a layman, I don't know anything about code, how can I learn, or how can I get into the astronomical stuffs, or how can I use the coding for my another set of research like solid state physics or something else. So computational is now going to rule the scientific domain in another couple of decades, right? So you may ask anything related to that in your research. Ram, there is a question in the chat.
Okay, how do we filter images of astronomical objects in Jupyter Notebook? Filter what? Meaning, you want to translate what to what? You mean you want to translate RGB to something? I mean,
So basically, we remove the dust particles and all, right, to filter it out to see the clear object.
mhm.
That's
So you should potentially be using a project called OpenCV. I'm typing that in the chat. I'm assuming you're already using it, right? So OpenCV lets you do all of this. But again, it's very hard for me to give a generic comment. But what you can potentially do is, at the very outset, what you have to do is to convert that into a skeletal image, right? Where you don't actually have uh, the visualized object, but only the skeletons of the object, right? And then you go pixel by pixel, right? Let's say you have a 64 by 64 image. You go pixel by pixel and frame out saying, okay, if my object or my dust particle is at this difference, again, I have to look at the data to define what is difference, right? But if you can potentially define that difference ratio, then OpenCV lets you point out or blank out these pixel values, and then you can convert that skeleton back into, I mean, you can basically overlay the skeleton on your actual image, and then what you're going to get is a dust-free actual image.
okay, sir. Thank you. I overall get the idea.
I'm sorry.
Also, do you conduct workshops as well?
We
For
do. Currently, we are doing things only on asteroid discovery and exoplanet, but we're very soon going to be launching one on technology and astronomy. Uh, yeah, you can probably just write to me on that email or write to Surendra on the email, and then we can probably send out a registration link, when the course is ready.
sure, sir.
Yeah.
Any other doubts, questions? So any other doubts do you have? Okay. So if there is no more question, maybe I can ask Ram about a few stuffs in decentralized. Yes. Someone want to ask? Who's asking? Okay. So if there is no more questions, maybe I can ask Ram to share a few words about the decentralization of astronomical education. Um, the first talk Dinesh delivered, right? So Ram's the one who is handling about the software part of ADL, Astro Digital Library, because so we are very much focused into astronomical education. So all of you all, I mean, you're all faculty members, I mean, teaching staffs. So you can translate this idea maybe to your students, your locality, or your institution. You can take it over. This kind of open project, like free and open source project. Free means freedom, not as such free. So this is free and freedom open source project. You may translate this into your, as I said, your locality or your institution, anywhere. So Ram, if you can give few idea about ADL, Astro Digital Library, how it can impact the institution, how it can impact the local community to learn science, to learn astronomy, and how it can benefit the entire nation building. So if you have few words to discuss, that will be quite interesting, I guess, before wind up the EVA session, fourth session of FTP.
Sure. Okay. I think Dinesh has given a good overview on what is decentralization, right? So I'm not going to go into what is decentralization. I'll confine myself to ADL only. So let's imagine a student entering an institution and they're connecting to your Wi-Fi and they have all of your lectures, all of the books, your reference materials, any other reference videos, audios, books, papers that you have published. Everything is available for the student within the Wi-Fi itself, right? And the student need not necessarily have internet for this, right? They just have to be on your Wi-Fi. So in a historical sense, many institutions have been doing this, meaning what the institutions would call it is they would call as the server in the college, right? Where all of this is put in and then everybody can access it in the network, right? Um, so largely that is really what we are trying to do. When you scale out this idea of a server to a community, right? How does the community really look like? Or how does the network look like? For example, if you go to a village, I'll take a village, maybe in any of the top of the hills, right, where you hardly get access to the network. There is a lot of fog. There's a lot of signal distribution. I mean, signal disruption. Uh, None of this is consistent. So then, how do you expect? So the larger question that we had was, how do you expect students from these places to even have access to internet? Right? Is that expectation even correct? That was really the question that kickstarted the ADL project, right? But slowly we realized there are two things we are talking about. One is education and access to learning resources. Two, access to communication, right? And what we are very clear is we are talking about access to educational resources, right? The question of do you expect students to have internet or common public to have internet just to watch or understand what is a star, the public or the student is just probably not going to do that, right? One, because it's important for us to understand the cost of internet. The cost of internet today ranges anywhere between 9 rupees to 19 rupees per GB of internet, right? And the poverty line is defined at 32 rupees a day. So we are expecting families, and the population percentage today is at least about 33%, right? At least by going by the government statistics, it's about 33, 34%. Now, what we're expecting is this 34% of families earning 32 rupees a day to invest 9 rupees or 19 rupees of internet every single day is just impossible to expect, right? So what we're trying to do with ADL largely is establish it in institutions and villages. Now, why is it important to establish this in institutions and villages? Is not a question of, oh, rural places don't have access to internet. Oh, urban places have access to a lot of internet, so we can do everything via the internet, is actually quite wrong, right? So tomorrow, what if YouTube shuts down? What if Google Meet shuts down? Are you going to say that, oh, I'll just find something else and move forward and lose access to all the knowledge? Is the larger question, right? So Dinesh broke it down to access and archive, right? Now, where ADL sticks is in this spectrum, that is availability of knowledge, sorry, availability of knowledge, accessibility of knowledge, and archival of knowledge, right? We're talking about all the three. Now, where is it available? It's available in the public Wi-Fi that's there. It could be your institution, it could be a village, it could even be an urban city, it could be one of those super big, super rich schools. It could be one of those government institutions. All you need is just a Wi-Fi router and one small server, right? And both of these are one-time installation. And once you put both of this, you have access to everything that's there on the server over the network, right? Now we talk about accessibility. Now, the very important reason why institutions are important in the whole project is institutions have access to infrastructure, right? And many institutions have already been working with local villages, local communities, helping them gain access to education or helping them gain access to, books, notebooks, or even basic livelihood. So many things institutions have already been doing among the communities that you have, right? Now, let's say institutions are going to go one extra step and establish this network. The whole village is going to have access to all the knowledge you're going to put in your server free of cost, right? No need of internet. Everything you want to teach to your students is available there. Any common public can access this. And anybody at any point in time, without the necessity of having to come to an institution, meaning if they can afford an institution or not afford an institution, would still be able to learn and grow along with this, right? That is what we mean by accessibility. Now, archive of this is when hundreds of institutions come together and start holding the same set of data. Even if one place, if the data is lost, the data is never lost. People can always copy it back from someone else and keep running the data, right? So it doesn't really matter if YouTube goes down or YouTube shuts down tomorrow, or it doesn't matter if people don't even know what is YouTube. They can have access to all the learning materials that you're putting through, right? Now, this is at the outset of it. How are we doing it technically? Is we are using um, usual Wi-Fi routers, what we call as commodity hardware, right? And a combination of a small server and Raspberry Pis. And depending on where are you trying to establish the whole thing, you may need about 2-3 Wi-Fi routers, or maybe 10-15 Wi-Fi routers, right? But once you have access to all of this, all you have to do is you have to keep on updating the knowledge/information. But two, what we do is a question of update. Let's say Jamal Mohammed is having a course and they are updating certain information. And let's say I am sitting in Bangalore and I want to update all the videos that Jamal Mohammed has updated, right? How do I do that, right? And remember, I'm talking about both of this without having access to constant internet. So what we are trying to do is to build what is called as a delay tolerant network or a sneaker net. Okay, this is the technical name of it. So what this does is we are going to be fitting small USB drives in buses, autos, and everything, right? And we will have one central point where there is access to internet which can download this data. Now you have one place where you have data downloaded, which could be Jamal Mohammed College itself. And then you have a village here, right, probably about 10 kilometers away, which has no access to internet. Now, what we are going to do is, the bus that is going from Jamal Mohammed or passing by Jamal Mohammed to this village will keep taking small bit of data, go to the village and deliver it. Again, it comes back, it takes small chunks of data and go back and deliver. right? This is what we call as a delay tolerant network. So when you use WhatsApp or Google Meet or any of this, these are not delay tolerant networks. Meaning the moment you send, the moment you see, right? There is no delay between them. And you receive the whole message completely, right? For example, if I type hello, if you receive H like this, E like this, E like this, L like this, and O like this, then it is delay tolerant network, right? And you may not even receive that instantaneously. You may receive H, E, L today and E and O tomorrow, right? But what we do today is this. We have the whole message delivered completely, right? So with delay tolerant network, that is really what we're trying to establish. I mean, this is already an existing protocol definition. We're just trying to re-implement the technicalities in a language and try to see how this whole translation can happen, right? And we are also parallelly exploring radio-based communication distribution because establishing a point-to-point radio is much easier. Instead of relying on delay tolerant networks, and there are a lot of citizen bands, for example, the 28 megahertz or the 5 gigahertz or the 2.4 gigahertz. Some of these citizen bands we can always reutilize to keep communicating and consistently sending data, again, without the need for internet, right? But the question really comes as long range. How do you communicate to data to a village that is at least, let's say, 100 kilometers away? That's really where we are finding challenges and where we are trying to see how do we establish point-to-point communications or delay-tolerant communications for data distribution, right? Which is largely a technical challenge, I mean, which we can currently solve. One person can just keep going there every month, take a hard disk, copy all the data and come back, right? It's a very simple solution to solve humanly, but it's not scalable solution, right? Which is where we're trying to automate. But largely what we're trying to do is we're trying to encourage institutions to use this idea called Creative Commons, okay, and free and open source software. Open source software, I think many of you would have heard of. It is open source software is basically when software source code itself is public and open, and you have the freedom to do whatever you want with it. Just like how I use Jupyter or Python, all of them are freedom softwares, right? So I can do whatever I want with it. So the idea of Creative Commons says that the article that you wrote or the book that you wrote or the video or the audio, whatever you're writing or creating, right, is available publicly for everyone to access and distribute, right? When we talk about copyright, or let's say I'm publishing a paper in IEEE or something, then what we're talking about is nobody can use it without the permission, right? You're free to refer it, but you can't use it without permission. But what you're talking about in Creative Commons is it is there, you're free to use it, you're free to redistribute it, but every time you do it, you have to tell that I am the one who has created it, right? You have the idea of credit. At the same time, you have the respect that knowledge deserves, right? Because it's publicly available. Everyone can use it. And what we are trying to do from ADL is to record much of this knowledge in Creative Commons. So, meaning there are already existing videos, audios, books that are there in Creative Commons, but there is a lot of things that's non-existent in this. So what ADL is trying to do is to create these videos, create audios, create books, definitions, learning materials, and publish all of them under Creative Commons, right? And at least in this project, we will be more than happy if institutions just come together, because we're going to be publishing everything out there free of cost, right? Everybody is free to download it, everybody is free to use it in their institutions, use it in their villages. And the most important aspect of the whole project is localization, which is we don't want more and more content in English, right? We want it, for example, in Tamil, we want it in Marathi, we want it in Kannada, we want it in Malayalam, right? There's no point in putting more and more and more emphasis on English, because it's hard for people to learn from it, right? It's a language of communication, I understand, but it's hard for people to learn it because it's not something that we do use every day, right? But versus the same thing available in their local language, they are able to understand it better, they're able to grasp it better, right? And all we have to do is just translate those words to English keywords for institutional education, examinations, etc. Right? But largely, ADL's focus is not being a first chance education, but to be a second chance education. Meaning, we are an assistive tool to help you understand, learn things, but we are not the ones that are going to replace colleges or schools. Right? So that is roughly what ADL. So what we're again. So in short, if you have to work out, we are looking for collaborations on who are willing to contribute knowledge in every domain, right? We are not saying only in physics. We are saying if you are a mathematician and willing to teach mathematics or chemistry or biology or botany or any of the basic sciences or astronomy or anything, right? Astro Digital Library is just a focused project on astronomy, right? The digital library is the largest project. And there we can have a computer digital library, we can have a chemistry digital library, right? We can have a mathematics digital library. All of this is just data, right? And there we are expecting institutions to come forward to help us work with you to generate many of this content, right? And publish all of them under Creative Commons, and help the whole world have access to knowledge, have access to learning materials without any kind of barriers, right? And if you're an institution who you think can adopt a village, or you already work with a village where you think we can establish a digital library, just let us know. We'll be happy to come down, visit the village, help you plan the infrastructure needed, work with you to distribute content, whatever we already have, whatever new you want to create. That whole process we can help you go through. Surinder, you want me to add anything specifically?
Yeah, I think it's pretty good, I guess. So again, the floor is open for questions or some discussions, if you have. Someone, if you want to understand better about the projects that Ram discussed about, or about the previous one, data related astronomy, data driven astronomy, let me say. Someone is hello. Okay. Anyone want to speak or discuss? Or do you have something related to astronomy if you want to speak? Okay, if there is no more questions, maybe I can introduce one more stuff that most of us we have discussed, right? Give words about asteroid search program. Yesterday also Dr. Priyagashan gave some glimpse about asteroid search program. Yeah, so this is about detecting asteroids. Okay, so asteroid detection is kind of citizen science program. Citizen science is nothing but who are all interested in science, but I'm not having much expertise in my subject or degree or whatever. You don't need that. So you're a citizen, you are loving science, you are ready to learn that subject, yes, it's for you. Okay, so also it's for students who are in the physics or mathematics or whatever science domain. They want to know about asteroids, or they want to work in the domain of asteroid search program. Okay, so this program is happening around the world. So this is mainly led by International Astronomical Search Collaboration. Currently we are working with them. I'm one of the actually I'm heading Space Generation Advisory Council, which is the United Nations Youth Office for Outer Affairs Youth Wing, let's say. So we are currently we are running a Tamil Nadu asteroid search program. Okay, campaign. It is a campaign currently going on. Around 10 teams of 10 teams are participating in that campaign. They are detecting asteroids. There are few telescopes in Hawaii. Actually, their names are Pan-STARRS 1 and Pan-STARRS 2. These two telescopes actually taking pictures of night sky. They are optical telescope. There are many telescopes. I'm sure you are aware of types of telescope. There are many types of telescope. One such telescope is optical telescopes. So these optical telescopes are taking pictures of night sky. Pan-STARRS 1 and Pan-STARRS 2 telescopes are taking from Hawaii. And these people, Pan-STARRS observers, scientists over there, they want to engage people in their research. In their research in the sense asteroid detection. Why we are caring about asteroids? That is a larger question, right? Let's say yesterday Dr. TVV discussed about it, because asteroids may have some potential elements which are not available in Earth, rare earth elements, let's say. So people are searching about rare earth elements, maybe which may present in some asteroids, or we can mine some minerals or water, whatever we can do that, right? That kind of stuffs. So people are searching for that also. Also, one more potential hazardous things are there, because asteroids may destroy the entire humankind, entire human life, entire living organism on Earth. Because yeah, 1 kilometer wide asteroid, not a 1 kilometer, maybe half a kilometer wide asteroid, diameter asteroid potentially can destroy everything on the Earth. Okay, so they can bring so much of radiation, and their power is like so much of atomic bombs. So people are really caring about asteroids, because in the earlier solar system, when the solar system formed actually, so there are a period called heavy bombardment era. During that time there are so much of asteroids, or I mean planetoids, hit on Earth or other planets. Say they destroy like anything. That's why we have craters on every planet in the inner solar system. So we have Mercury, Venus, Earth and Mars, right? All these planets are so many craters. The very good example is our moon. Moon is having so many craters, right? The craters are wide and everything. So yesterday TBV said that we can use the craters as a radio antenna for detection. Like we have so many craters. So these craters are because of the asteroids or planetoids in the earlier solar system hit on the planets. So similarly, still we have so many asteroids. See, the thing is, we have detected few asteroids, but that is not enough. Still, there are more asteroids we have to detect. There are asteroids very close to Earth. They are called as, they are named, and in general, they are named it as near-Earth objects, near-Earth asteroids. So in that classification, near-Earth asteroids, there are few categories. One such category is potential hazardous asteroids that may cause really destruction on Earth. So people are searching, trying to find such potential hazardous asteroids. So they are, whatever telescopes working or focusing on asteroid detections, they are giving open data to the public. They can come and come forward to take part of the research, asteroid detection research. Okay. So the beauty is, if you have detected an asteroid, you can name that. That is the real beauty. You can name that asteroid the database which is maintaining by the International Astronomical Union and Minor Planet Center is maintaining the database of asteroids, whatever people are detecting. Also the comets, about the comets, they are maintaining the database. So when you have detected an asteroid, you can name that asteroid with your name, and the database will be there. Okay. So we at Chiguru, we have detected 4 asteroids right now. Maybe yesterday during the inaugural session, Hattori sir, Dr. Jamal Mohammad Jafar shared the names of asteroids. So we are in the list. Still, we need to identify the parameters of asteroids to get the orbital stuffs and everything. So once that everything determined, we are ready to name it. So this entire process will take some time, but during the detection process, it's really amazing learning. So you have to work with the software training and everything we can take care if you're really interested. And the students from actually currently at Jamal Mohammed College, they have formed a team inside the Astrolab. So we have a Astrolab in Jamal Mohammed College Physics Department. So there are 5 students actually going to participate in asteroid search program that is going to happen in upcoming months. So they can work with the software, and they have to detect some moving objects, and they need to identify some parameters which is applicable to measure whether that moving object is asteroid or not. So once they determine it, we need to report to the international team. So this is kind of a simple process. For this process, hardly you need to spend 2 to 3 hours per week. That's it. But you can learn many things about asteroids and minor planets. That's a mind-blowing job. So this is the one thing I really want to introduce, because last 3-4 sessions we are constantly speaking about asteroids and asteroid detections, everything, right? And one more thing I want to bring, there are a few hands-on stuffs in the pipeline, hands-on workshop kind of stuffs in the pipeline. The one thing is telescope building. The optical telescope we can use in the ground, use on the ground, because we can't get X-ray into the ground, because our atmosphere will filter the X-rays and harmful radiations away, which are coming from the universe. Our atmosphere is filtering that rays. So that we need space-based telescopes like Hubble, Kepler, and Chandra X-ray telescope. All are in space. So we can get clear sky, without light refraction or scattering. We can get a good amount of lights to observe the celestial objects. So that's why people are building space-based telescopes. Similarly, we can build ground-based telescopes, like optical telescope, radio telescope, and everything for hands-on trainings or for initial stage research. Let's say you have a first-year students who are interested in physics, deeply in astronomy and astrophysics. They can get into that pipelines, can learn telescopes, optics, and radio physics, radio astronomy. They can build their own telescope to detect some objects. Let's say if someone is focusing on stellar astronomy, let's say heliophysics, about studying about sun, they can build a radio telescope to detect sun. They can observe various patterns of sun's radio emission. They can record it and they can publish some paper, because nowadays there are many options. Students can write their own discoveries or their own idea into public. Okay. As Ram said, you may encourage your students to write some scientific stuffs in the Creative Commons way, Creative Commons structure, where everyone can consume without paying a penny or something. Okay. That kind of stuffs also you can engage your students, building radio telescopes and optical telescopes. So we are having some programs in our pipeline. You can use that, building radio telescope and optical telescope. So this also I want to bring into your picture. And a few questions was there. Is there any hands-on workshops or hands-on programs where we can engage? By your own, for your own learning or for your students? Yes, there are few programs. One such programs currently we are building as data-driven astronomy. We can you personally can learn those subjects about data, Python, the Jupyter notebook. If you're not really interested in, if you're interested, but I'm not really aware about the coding and stuffs. I don't have any pre-knowledge about computer science. That's fine. Still, you are interested in science, interested in astronomy. You can really learn the subject. So Ram is the one who is handling all the stuffs of computer and Python programming coding. So he has very good expertise in that subject. He's been in the teaching, Python and computer training programs for the students. He can teach in a downtrodden way, down to earth way. So you can learn from him during the workshop. So that is one more thing I want to bring into the picture. Yeah. So I think most of the stuffs me and Ram have covered, I guess, in the technology and astronomical related astronomical data stuffs. So if anything in your mind,
Excuse me, sir.
yeah.
How we can participate in the abstract program?
Asteroid search program, we will open the registration. Maybe you can follow the, you can send a mail. We can give the details to you. You can get into the program. So that is one part. Otherwise, there will be one open campaign for the students. We will announce widely in a paper and other blogs and on your website. You may check into that, or just wrote a mail. We can give the details.
So, sir, could you pin down the email in the chat box?
So you have Ram's email, right? In the chat. No problem. I can give my email.
Yeah,
So
yeah.
already Ram put his email. Just wrote a mail to him. That's fine.
Okay, sure. Thank you.
Thank you. And one more important thing is, we don't know all of you are from physics background. Somebody can from maths background or chemistry or biology. The astronomy is the subject you can involve all the basic sciences like mathematics, chemistry, biology. There are subject called astrochemistry. There is a subject called astrobiology. You can search about habitable zones, aliens. Let's say aliens. Okay. Yes, really, people are involving in that subject and detecting the biomolecules which are available, which may available in our universe somewhere, in some other galaxy, in some other star system. So people are searching in that domain. Astrobiology is there. Currently, it's getting the good scope because we are going to colonize some of the solar system objects, like let's say moon and Mars. You need biology there, right? So you need medicine, you need plants to grow, you need food, you need maybe sometime if you are injured you need surgery and everything. So there are few groups in the world, in our world, getting involved in astromedicine, astrosurgery kind of stuffs. So that is really having a good scope in near future. And astrochemistry already in the picture of astronomy, because we need to detect about the spectrum of various elements which are present in our universe. So people are searching about it. So the astronomy is having a wider scope in for the all basic science students, all basic science teachers groups. So this is also I want to bring to you. And I can say one more stuff. In India having a one space-based telescope, let's say, or satellite, that is called AstroSat. Yesterday, Dr. Priyasan discussed about it, right? AstroSat. AstroSat was launched by ISRO. Still, it is working. They are having a data. They are producing data. That telescope, that satellite is continuously giving data. ISRO every year ISRO opening some call for those who are working in the astronomical domain, or those who want to work in the astronomical domain. You may write a proposal to ISRO to receive the data, and you can work with your students. You can publish, or you can produce some good paper, good quality paper, let's say. So ISRO is giving for free of cost for the students and faculties who are in higher education domain. So that is a really good opportunity for you people. You may explore. If you want to get into that process, maybe I can help you. We can help you to the process. So that is one more option I want to bring into the picture. Yeah. So there is just a course for material science students who are actually interested in astronomy. Yeah, there are few playlists in YouTube, and also there are few courses in material science related astronomy. People are searching about the origin of elements. So the origin of elements means we are searching about chemical elements in the universe, right? How these elements are formed in the universe, that is larger question, right? So maybe I can RAM physics. Maybe I will get your email ID from the database, and I will drop a mail with few reading list and materials. You may receive that. You may go through that. So if you want to ask anything to me or to Ram, the floor is open for you for another couple of. I mean, we have some more time. You may speak. You may ask. No problem. Good. Anything do you want to speak, or any doubts, or if you want to share something, you may also have some resources like as I gave to you. So சார் சொல்லுங்கள் சார் சார் சொல்லுங்கள் சார் அடுத்த செஷன் வந்து அவரோடது 12:30 தான் சொல்லியிருக்கோம். அவர் 12:30 தான் ஜாயின் பண்ணுறேன்னு இருக்காரு. மேபி நம்ம ஒரு ஓட் ஆஃப் தேங்க்ஸ் மாதிரி சொல்லிவிட்டு ஏதாவது டவுட் இருக்கான்னு பார்க்கலாம். இல்லை அப்படின்னா ஒரு ஓட் ஆஃப் தேங்க்ஸ் வச்சுட்டு இதை முடிச்சிடலாம் சார். இந்த செஷன் முடிச்சிடலாம். அடுத்த செஷன் ஒரு 20 minutes ஸ்டார்ட் பண்ணிக்கோன்னு சொல்லிடுங்க சார். ஓகே சார். நான் அப்படியே இப்போ முடிச்சிடுறேன். நான் இப்போ அப்படியே முடிச்சிடுறேன் சார். நீங்கள் அதுக்கப்புறம் அப்படியே ஓட் ஆஃப் தேங்க்ஸ் சொல்லுங்கள். Okay, so if there is no more questions, we may. Okay, there is a question. Dear sir, next time please conduct a session on gravitational waves. Yeah, sure. We have a Astrolab talks in our pipeline. You may attend. This is open for everyone who are interested in astronomy. So we will bring various astronomical subject in the series. So you can attend all the talks, gravitational astronomy, radio astronomy, even dark matter physics, dark matter astronomy, dark energy related, and high energy physics. So there will be many topics in the Astrolab talks. You can attend those series. We will drop a mail about that also. Yeah, surely we will get into the topics and Astrolab and everything. Yeah. Gravitational astronomy. So like Ram physics have shared something. If you want to speak something, or if you want to converse something about astronomy, you may speak. If there is no more questions or no more conversation, we may end this session. Those are in YouTube. You can also post your questions or discussions.
Sir, where we need to mail to get the data from ISRO of Astrostat?
Are you a professor? I mean, teaching faculty or a student?
I'm a student, sir.
Okay, so first you need to get your teaching faculty. I mean, your teaching faculty have to write a mail or have to submit a proposal to ISRO. That is, you may just check ISRO website. There will be an option called AstroSat. You may ask your teacher if he's really interested into that subject. You may ask your professor to write a proposal. So once you wrote the proposal, they will analyze it and they will select and give the data.
Sure, sir. Thank you.
Thank you.
Thank you, Ram sir, for a nice presentation. You have explained detailed information about astronomical data and technology. So once again, thank you for joining us and delivering a wonderful session. So next we come to the end of the session too. It's a time for formal vote of thanks. I request Mr. S. Muhammad Ibrahim Sulaiman Seth, Assistant Professor of our department, to propose a vote of thanks for session 2.
Good afternoon, one and all. I take this opportunity to propose vote of thanks for this session. I would like to thank our resource person, Mr. Ramaseshan, Head Research and Development, Chiguru CoLab, Bangalore, for delivering an excellent lecture on astronomical data and technology. Thank you, sir. Sir highlighted the utilization of astronomical data for location identification of sun and moon and asteroid diameter prediction using astronomical data. So I hope these are very useful for all the participants. So once again, I thank you, sir, for your nice presentation. Next, I would like to thank our head of the department, Dr. M. Jamal Mohammed Jafar, sir, who has given constant encouragement and invaluable support for organizing this FTP program. Next, I thank all the participants for the effective utilization of this session and interact with the resource person. So I thank resource person, all the participants. Thank you, one and all.
Dear participants, next session, session 3, will start by 12:30.